The TAs should still have theirs, of course. And that's just for the one day. So any questions about the lab? Yeah.
I'm having a hard time understanding how to get the variable arity inside the width and lambda
Okay,
stuff.
remember it's not variable arity. We're not writing variable arity functions. We're writing fixed arity functions that could be of any fixed arity.
Mm-hmm.
Does that make sense?
Yes.
Okay. So that distinction is important.
Okay.
None of these are variable arity functions. They're fixed arity functions, but the user can declare multiple parameter functions of any fixed arity.
Okay.
Okay? In other words, a particular function has to have 3 parameters, or has to have 5 parameters, or has to have 1 parameter. You can't pass an arbitrary number to any particular function.
Mm-hmm.
So the big thing there is, let's actually go back to the CI3 interpreter. We'll go back to this in a minute. So for that, function definition would no longer have to store a single formal parameter. It'd have to store a list of formal. If I was to do this, I'd change this to formals, and it'd be a list of symbol.
Mm-hmm.
Besides having one single arg expression, it will have a list of arg expressions.
Okay.
Okay, so it'd be a list of AE. Sorry, an array, pardon me. You actually store these just using Julia arrays. So this would be an array of symbol and an array of AE.
Mm-hmm.
Okay. Then in the function definition node, sorry, when you're parsing, you would still store, you'd still store, instead of a list of, expression 2, instead of that being a single symbol, this will now be an array of symbols, so you'd store that.
Okay.
Okay, and then likewise, you'd still parse the first expression, that's your function expression. You would recursively parse all of the rest of the expressions, and that becomes your list of arg expressions, or your array of arg expressions. Okay. So this is where you can use slice notation, 2 to the end. You could basically map parse onto it, or write your own little function to loop over it, whatever you want to do with it. Remember, Julia has its own for on an array, so basically it's just for each thing in this array, parse it, and then get an array of the results. Everybody okay with me to that point? All right, and then when you get to calc, instead of storing a function definition node, and when you make a closure, so when you build when you have a function definition, you build a closure, instead of storing one formal parameter, you'd store the list of formal parameters from the abstract syntax tree, and then still the same body and current environment. And then here, when you're actually calling the function, you'd still evaluate the function expression to get the closure. Instead of having a single actual parameter that you get from evaluating the one arg expression, you'd have an array of actual parameters that you get from one by one recursively calculating each of the argument expressions. You build your closure. Now here, in your environments, the lab says there's 2 ways to do it. There's actually a bunch of others, but 2 straightforward ones. So in a closure, or in an environment, we currently store a single symbol, a single value, and a parent environment. There's 2 ways you can do this. By the way, this part of it also applies to a with, and we're going to talk today a little bit about the connection, or possibly Wednesday, about a closer connection between with and function application. But in a with, you'll notice you're just making one call to extend environment, binding the single symbol to the single value. This now could be, everything I'm describing here is going to have a similar change in with nodes. By the way, one of the things I would do to start is don't worry about changing with and function application and function definition. Just graft in your stuff from the previous lab so that it works with the current ret vals and stuff like that. Because there's some, you can graft in your old stuff, but you're gonna have to change where you do bin op. Remember how with plus you had to recognize the return values were num vals? You had to check and make sure they were num vals. You had to then pull the values out, you had to add them, or do whatever the operation is, and then wrap them back up in a num val. So that part, I would just get that all working first. I would make extensions, then I'd look at just pick one of the two. Just maybe start with, so you get the extended environments correct. Don't worry about multiple parameter functions. So in other words, the big thing is don't try to bite off the whole lab at once. Don't try to make all the changes to the parser and then all the changes to count. Change just so bring in your old stuff and change so that it collapses the binary operations to a bin op. Graft in the stuff for callouts and unary minus, however you did in the past lab. Then change width to have multiple bindings. And then once you've got that working, change functions, both definition and application, to have multiple parameters. You see the idea?
Could you remind me why we're returning num vals again?
So it used to be the only type of data our expressions could return was number. So we didn't bother checking, right? When we recursively call calc, it's got to return a number. But now it can return a closure as well. And theoretically, we could extend this to add strings and all kinds of other data types to the language. And so retval is a data type to represent values in our target language. And right now they come in two flavors: num vals, or numbers, or closure vals, for storing closures. Okay. So with environment, just popping back sort of from that interrupt there, we bind a single symbol to a single return value, and then environments always extend other environments except for the empty environment. So the simplest way to do this is leave the definition of extended environment the same, and when you have multiple bindings in a width, just make multiple calls to extend environment. So start off with your current environment, take the first binding and extend the environment with that. And then take your second binding and extend that environment you just extended with that one. Does that make sense? So you're basically just creating a chain, one for each level. Instead of a separate environment for every scoping block, you're just creating a separate environment for every binding within scoping blocks. And scoping will still work out straight. That's probably the most straightforward way. The other way that you could do it is just change the extended environment itself. So instead of storing maybe instead of val, it becomes vals or values. Instead of storing a single ret val, maybe you store, instead of a single symbol and a single value, maybe you store a dictionary that binds symbols to ret vals. Does that make sense? There's lots of data structures you could use that way. You could have an array of symbols, an array of values, array of ret vals, and then you do your own lookup in the array and then find it. That's what dictionaries were built for. So, and the key idea though is you can do one in each environment and then just chain multiple ones together for a multiple binding width or a multiple parameter function call. Or you could just sort it so each environment, each scoping block has a single environment, and then environment stores multiple symbols and values. Is that clear? So now what you would do here is instead of an extended environment to bind the one formal parameter to the one actual parameter, you'd use either of those two strategies to bind each of the formal parameters to their respective actual parameter. By the way, that also implies, there's a couple things implied in there. One, what's returned here from what's returned here from this expression, recursively calculating the function expression, we're calling it closure val. You'll want to check and make sure it is, the type of that is closure val. before you start diving in and getting fields out of it. Then also, you will have, remember I said you're going to want to bind each formal to its respective actual parameter. Well, just make sure that the number of actual parameters matches the number of formal parameters that the function was declared with. Or in code, that this closure val, that it's suppose you stored a list of symbols for the formal parameters, so that its formals field that array has the same length as this arg expression that's stored in the abstract syntax tree. And you can check that actually right here between these two. Before you ever recursively calculate all the actual parameters, you can just look at the length of that array to tell you how many there are. Everybody okay on that? So it has to be a function, a closure, and the number of actual parameters had better match the declared number of formal parameters. That's why I was emphasizing its fixed arity, because each function has exactly some number of parameters, and when you call it, you must provide exactly that number of parameters. So the reason for taking time on this is I suspected that your question, that you were not alone in your question. Was this hopefully time well spent? Okay, I'm seeing some nodding. How many have finished already, or close to? Okay, so hopefully for every, since that was a very small number, hopefully this was time well spent for all the rest of you. So let me just circle back and just, did that make sense, the explanation I was giving with it? Okay. Again, don't try to swallow the whole assignment at once. Just make the change to bring in the other functions that you did for the first lab and get binop and stuff working. Then try to bite off the multiple binding width. That'll force you to get your environments right, and you'll be used to doing things like looping over the array of bindings and and building the appropriate environments. And then I would try taking on the functions. Yeah.
So are we like porting our old code into CI3 or this CI3 into our old code?
I would use CI3 as a base because it already has environments and ret vals. Otherwise, you'd have a lot more. The amount of grafting is less if you take what you did first and pull it in than the other way around. Now, you can't just bring it in unmodified. You will have to look at what CI3 does with, say, plus nodes and minus nodes in calc, where it's actually checking to make sure the results left and right are num-vals, and then doing the add, and then, sorry, it's not actually doing the checking, but we talked about how to do that in class. Actually, I think we need to get to that for one. So check that, because you'll bring that in and you'll have to tweak that. But once you've got that working, now you've got a good base for saying, okay, I'm going to add width. And so width will force you to either, so it may or may not require you to change the environment, depending on which of those strategies you choose. But you will have to visit this width node, because now you'll have an array of bindings. It'll force you to change first the parser. So you'll have an array of binding. So you'll have multiple. So for each binding, variable and then sort of initialization expression or binding expression, you'll have to evaluate that binding expression, add that variable as that value, or that ret val, to the environment, either by chaining it or just adding it to the dictionary in the environment that you're currently building. Actually, sorry, build up the dictionary first, then make the one call to extended environment. Questions? Did that help? Okay. All right, any other questions? Okay, let's dive back into the code, actually. Oh, sorry, just looking ahead. So we have, so last time we started talking about recursion, but I wanted to spend most of the time actually walking through an example of what happened before we started looking at recursion. that hopefully was helpful for the lab, but also laid the foundation for why recursion broke. And so I'm going to pick up at that point, and then we're going to talk about how you actually fix it. It's a one-line change in our implementation. It could be different depending on other strategies. I want to go back. We talked about parser generators actually earlier, and I want to show you something before we leave scoping, that in terms of functions and recursion and stuff like that. I actually want to show you that some of these ideas also apply in object-oriented languages with both fields and data members and methods. So I'll show you an example there. Then we're going to get to program analysis. Program analysis will start today. We'll likely carry this over till next time. And that's going to be the foundation for we're going to build the CI4 interpreter that will be the basis for interpreter 3, the last interpreter assignment you're going to do. After that, we're going to get into some other things while we're still talking about how interpreters do things inside, but those won't be part of what you're actually going to be needing to implement or build on. Okay. All right. So let's go back to, actually, sorry, let me go back here. All right. By the way, just as I was walking out of the house, a big drop of water hit like right on my shirt from the roof. And it still can't get that dried. So, all right. So we ran an example, like this is a slightly more complicated example. Last time I wrote a recursive function with the CI3 interpreter, we walked through first with a non-recursive function. We saw what happened. Last time I just wrote I called the world's dumbest recursive function. Like f of x calls f of x. This is a slightly more complicated example. It's just simply, this is a summation function in our language. So you give it n, and it will give you the sum of all the numbers from 0 to n. Or 1 to n, if you prefer to think of it that way. Now when you run this, because of this recursive call, so it's just simple. F is a function that takes a parameter n. If n is 0, return 0. Right, sum of 0 to 0 is 0. Otherwise, return adding n to the result of recursively computing the sum from 0 to n minus 1. So a very straightforward, simple recursive function. We call it for f of 5, and we get undefined variable f. And what we were talking about towards the very end last time is that what goes wrong, can you guys see the green? I know green is a lousy color for whiteboards. That's why I don't use it as a main color. I'll use it as a highlight or difference or accent color. But it's all I've got. So can you guys see this okay? All right. So remember that what happens with the execution, I'm not going to go through everything again, but the heart of it is that we start off in an empty environment. We define the function which creates the closure that remembers the environment in which it was created. And then we take that anonymous function and we give it a name by building a new environment and say, all right, the name of that function is bound to this closure, and this environment extends that environment. Now what happens is when we call that function, we create another environment here that's going to bind, sorry, in this case I think it's n, binds the formal parameter, in this case 5, and here was the key thing. Remember that with static scoping, the environment we create to bind the formal to the actual parameter is always the environment that's stored in the closure that we're applying, or for the function we're calling. Well, that environment we saw was, I'll draw it this way, that empty environment. And so in this environment, we're now evaluating this body. When we get to referring to n, that's fine. We can see n. But when we look here for the recursive call to f, we look here, there's no f defined. We follow, there's no f defined here, we get undefined variable error. Okay, so that's what was going wrong last time. What we talked about at the very end then is, the problem is that we created this closure anonymously. And so if you just think about it intuitively, how can you create a recursive anonymous function? Right? How does it call itself if it has no name? Even if you give it a name later, that doesn't actually make that work. Another way of thinking of it is the way with works is it always evaluates this binding expression, this initialization value, in this case getting this anonymous function, and binds the name to it. So there's a couple ways you could do this. So first off, let me mention as a slight digression, there actually is a weird way to have an anonymous function call itself. Right? It's called a Y Combinator. I'm not going to go into the details of it, but since it was actually mentioned in a note on Piazza, I wanted to at least just give you a brief intuition. So a function can't call itself by, an anonymous function can't call itself by its own name, right? But if it's passed a function, it can call that function, right? Because scoping wise, that's just, it can call it by its name, which is its formal parameter. So what if you pass to a function as one of its parameters itself? It can now actually call that, or it's really a copy of itself that does the same work, but it effectively can make that work. Now, the problem is, how do you pass an anonymous function to itself? Because you can't actually do that. Well, what if you had another function outside that into which was passed this anonymous function, and it then invoked that function through its name, its formal parameter, it defined in that outer function, and passed the other function. So in other words, you actually end up sort of calling the function with itself, right? It's a weird thing. If you got that, great. If you didn't, don't worry about it. I just wanted you to mention, I just wanted to, in all honesty, mention there is a weird workaround. And yes, it's weird. If you want to look up more, it's called a Y Combinator. Right? Again, if you don't get it, totally fine. This is one of those let him who hath ears to hear kind of thing. All right, so going back to this, let's assume if you're not going to do something weird like the Y Combinator, what you basically have to do, though, to make recursion work then, is that the closure, because it's going, when we eventually evoke the function, it's going to call itself recursively. It has to be able to see within its own scope. The function has to be able to see its own name within its own scope. Everybody understand that thing? So to make recursion work, a function has to see its own name within its own scope. And that means we have to do this. That can't work. So an environment says this variable is bound to this function, but this function has to store the same environment in which its own, or this closure has to store the same environment in which the function's own name is defined. Now syntactically, that you can, some languages will actually use a different piece of syntax where you have to give it a name, and so then it actually builds this recursively. But if you don't use that special syntax, it'll just do the normal. Racket, by the way, does that. It has a construct like our with that's called let. It has another language construct called let rec. It's a recursive form of rec, or of let. We'll actually see this later when we get to Haskell. It has something similar. So you can do special syntax. You can also do it with our current syntax by recognizing when you're building the with, or doing the with, if the thing you're binding a name to is a function, then you have to build this circular data structure. Now here's the problem. Just think about this in C++ or Java. If I have one object that refers to another object, or object A refers to object B, and object B refers to object A, which one do you make first? You have to make one or the other first, right? So let's suppose you make A first. All right, so then you build B to refer to A, but oh, except A didn't refer to, you can't make A refer to an already non-existent B, or not existent yet B, and vice versa. So anytime you build any circular data structure in any language, you have a chicken and the egg problem. So in this case, except for the Y Combinator, which is sort of a third option, you're basically left with a strategy that is to sort of stutter step the creation, right? Or in other words, create a partially complete chicken, create the egg, then go back and patch up the chicken, or vice versa, right? Okay, I'm really abusing the metaphor, but you get the idea. I can build the environment. One way to do it is build the environment, and for its value, I just put a dummy value there. So I can recognize, oh, this is a width. I'm going to create this environment with this variable, but put in a dummy value. And then I'll create the closure to reference that environment, and then I have to go back and patch up this environment. So going back to the two objects in any language, I can build A first, then build B, then go back and patch up A to refer to B, or vice versa. So the other option is build the closure first, have it extend this environment, then build this environment here, the new environment with the width, and then go to bind to the closure. At that point, it's everything we've done, and then we can go back and change this environment field to point not to the previous environment, but to the newly created environment. That's what has to happen again to make recursion work. So we can actually do this with the following changes. So distributed through Learning Suite is the CI3 interpreter. It has two lines different, one in the declaration, one in code. The declaration is just simply, when you declare data structures or structs in Julia, by default they are what is called immutable. So this is a term we're going to come back and talk about much more on Wednesday and Friday. When you talk about mutation in a language, okay, this is not X-Men, this is not anything else like that. This is mutation is changing the value of a piece of data in place. Okay? And so things that can be changed in place are said to be mutable. Things that can't be changed are said to be immutable. And so by default, these structs are immutable. If we add the mutable keyword on, it simply says, you can actually go back and change the value of one of these fields later, which we're going to do. We're going to take the second strategy of patching up the closure. So first off, we just have to make it so it is, declare it so it is mutable. And then inside the with node, we're going to add, all right, I said one line, but it's really these three with the if. So we're going to add these three lines here. So starting with this if, all we're going to say is, so we're always going to evaluate the binding expression. In this case, that's the closure. We'll always build a new environment that binds the variable to the binding expression. Then we're going to do one more check. And the check that we're going to say is, if the thing that you just gave a name to is a function, in other words, its type is closure val, let's go back and patch up the environment. Remember, this binding val is this closure val. So let's go back and change the environment in the closure to point to this new environment that we just created. See the idea? So you have to go to some, the point is that you have to go to some extra work to make recursion happen if you're doing static scoping. Okay? And notice I qualified that by saying if you're doing static scoping. Do I have to do any work to make recursion work, or anything extra if I do, to make recursion work if I'm doing dynamic scoping? So why not? Yeah.
But if it's looking back in the variable tree, then it'll find itself.
Right. So in other words, remember with the static scoping, we're not bothering to store the environment in which this function was created. when we call the function, we always extend not the environment that was in scope at the time the function was created, that's static, but the environment that's in scope at the time the function's called. And so if the name of that function is in scope to call it in the first place, it will still be in scope within its own body. Does that make sense? So in other words, you're always back. Remember, the question comes up when I encounter a free variable, in this case a recursive call. The free variable is it's the function's own name, because it's not one of the formal parameters. And so, so the idea is, instead of looking in with static, you look in the scope in which it was created. Dynamic, you're just going to look in the caller's environment. And of course it's going to be there in the caller's environment. It had to have been for me to be able to call it in the first place. So notice, when we talk about static versus dynamic, you all said, oh yeah, static's that's kind of the way to go because it was what all the languages you used did. You're absolutely right, but I wanted to point out, we've had to do along the way some extra work. We have to store the environment in the closure. We have to make sure to extend the correct environment, the environment from the closure when we call the function. And then we still have to do some extra work to make recursion happen. So it is totally worth it to make static scoping happen. That's the right way to do it. But you have to do some extra work. Okay? Yeah?
Is static scoping something unique to Julia, or is
No, that's what I'm saying. Every language you've used, use static scoping. Every single one. It's a bit of a non-issue in C++ because you can't have functions defined in other functions. But in other words, the only thing that's in scope when functions are created in C++ is global variables. But there are language, in other words, so C++ is still static. It's always the global environment. Right? Not by choice, but just because that's the only environment that's in scope when functions are created. In other languages where you can actually create and returns, or where you can declare functions inside of other functions, every one, other than a few really old languages before we learn better, or a few that are very simplistic string substitution kinds of things, everything else uses static scoping. So C++, Julia, Python, JavaScript, PHP, Perl, Ruby, everyone that you want to look at, they all use static scoping. And so does Racket and Julia. So do Racket and Julia. All right, so let's talk about another issue with scoping, especially since we're talking about some of these other languages. It turns out this question of scope also shows up with the same static versus dynamic terminology in object-oriented languages. So this is C++. Hopefully you recognize that. So consider the following. I'm going to define a parent class. In this case, it's called A class. It has a public data member, an integer x, and then it defines the following methods. It has its own constructor. So when I build something of type A class, it sets x to 42 to initialize it. Then I have three methods. One called getXA that returns x. One that's called getMyX that also returns x. You'll see why in a minute. And then another one called getTheX, which calls getMyX, which returns x. And then that x should be this one, right? Does everybody agree that that's how it should work, just looking at A class? Now let's look at B class. So now let's define a child class. A child class can define its own data members. It can also, by the way, give those data members the same name as the parents, in which case they're actually unique instances. They're stored separately. This one, think of it scoping-wise. This, within class B, this x shadows this x that inherits from the parents. So you guys know, of course, classes or objects, they inherit all the data members from their parents, plus they can define a few more. It's entirely possible to shadow those. Okay. So now B class's constructor sets x to 99, which x?
Local X.
The
Its
one that
own.
inherited from its parent or its own?
Its own.
So,
Okay, that was kind of what you would think, right? And that's actually what it does. Now, get xb returns x. Okay. We're going to get to that same question of which x in just a minute. I'll show you. And then also get my x returns x. It does not actually override get the x. It just simply inherits it from its parent. Everybody okay on the class declarations? And I know this seems like a weird contrived example, and it is, but these situations actually happen in real life in object-oriented programming, quite often actually. All right, so now we're going to declare an object of type B class, the parent class. Okay. All right, and then, okay, I'm old school, I still use printf, all right, but so I'm going to call, and here's the important thing, this is just printing out for readability. I'm going to call B, and I'm going to call getXB. Okay? So getXB is that method. GetXB return x, which x?
99.
Okay? Everybody agree that that should probably be this one that was initialized to 99? Okay. All right, now, let's call the method getXA on object B. So object B has these methods, but remember, it inherited these from its parent. Let me scroll this down so we can see it. So all of these methods, so getXA it inherited, getMyX it kind of overrode, scoping-wise, or shadowed, and then getTheX it inherits as well. So let's take our object of class B, and let's call getXA on it. So getXA returns x. Which x? Not 99? I mean, you're invoking this method on an object of class B. Isn't class B's x 99?
Yes, but it inherits that function.
yeah, that function.
Okay. So it inherited the function, but then that function represents data members. Are you sure it should be accessing things in class A and not class B?
That function never access.
Pardon?
I want to say that function never have access to the class B space.
Ah, okay. So first off, you're right. I'm just trying to challenge you as to why. Part of you were mentioning, do we really want class A to have access to class B's data? Should a parent, children should be able to access data members from the parent, right? Should it be able to go the other way around? Okay. Also, when you were kind of alluding to, I'm just going to show it this way. When you wrote class A and I later extended it with class B, which one did you mean for it to return? Right? Clearly, this call was meant to return that one. So I'm going to give this question, I'm going to give names to these options. The question here is, when I invoke a method on a particular object, does it use, and especially when that method is inherited from a parent, does that method, so the question now is, getAX, does it use X that was in scope when this method was created? Or does it use the X that's in scope when the method was invoked? In other words, the current class. Do you see the issue? So when a method references data, do you first look in the current class and go up the hierarchy? Or do you look in the class that defined the method and then go up the hierarchy from there? Yeah.
The class that defined the method, but if you override the function, then I think it's different.
Okay, so we're going to get to the functions too. Right? Yes, so if I had overridden the function, so for example, by the way, if I call get my x on B, it will definitely return this one, because it's going to find this method before it finds this method, and this x returns this x. So if a method references data, when it goes to look for the data, if it looks first in the class that defined the method, not the class of the current object on which you're invoking the method, but if it looks first in the class that defined the method, that's said to be static inheritance. If it looks first in the class or for the object on which you invoke the method, in this case class B, that's dynamic inheritance. So we use the same static versus dynamic term.